All right, so in this video, we're going to talk about electron configurations, and we're going to need to start by remembering some of the basics from the Bohr model. The Bohr model presents the idea that electrons can reside in specific energy levels or shells, called n equals 1 for the first shell or n equals 2 for the second shell. And of course, we learned that Bohr learned about electron behavior by studying emission spectra, or the light that electrons emit when they transition from a high energy level to a low energy level. They release light as they lose energy in that transition. But Bohr's model, it turns out, didn't apply very well to multi-electron atoms. It really only applied very well to hydrogen. And this is showing the emission spectra from hydrogen, but a more sophisticated model was needed to explain multi-electron atoms, emission spectra and electron behavior. So the Bohr model had some shortcomings. It really was only partly correct. But essentially, the model went from a planetary model to a quantum model. And one of the key differences here is instead of thinking about electrons as objects like planets are that orbit the sun, we're going to think about electrons as probability waves. So this is trying to show that the electron is a wave phenomenon, but it's a probability wave, which is a pretty sophisticated idea. And some of the experiments, like I said, that are employed here to give us this evidence are a little bit more complicated than we need to consider, but we do need to consider the outcome of those experiments, which is the development of this idea of an orbital. And an orbital is not the same thing as an orbit. An orbital is really just a three-dimensional region of space where you're likely to find an electron. Sort of like the blades of a fan when they're spinning occupy a region of space that's sort of undefined, and really best thought of as a probability. The orbitals are probability density distributions. They're kind of like probability maps, but they have some very strange shapes, as you can see in this picture. So we're going to introduce the concept of orbitals, and we're going to expand upon Bohr's model, which really only included one level of an electron's address. In other words, the idea that electrons exist in shells. Well, it turns out that's only part of the story. So here's how we're going to summarize these notes. In our written notes, we're going to first make a data table by dividing the page in half to make a very large right-hand column, and then dividing this in half again to make two smaller left-hand columns. And we're going to be introducing the idea that there are four quantum numbers that describe an electron's address. And so far, we've really only learned about the first one, which we call the principal quantum number, and that is what we are referring to when we use the letter n. So for instance, n equals 1, n equals 2, that is the principal quantum number. So we're going to label this quantum number, and the first one we're going to talk about is n, which is the principal quantum number. Now, there are four quantum numbers, so let's go ahead and make four rows here, just dividing the page equally. And you can think about these four quantum numbers sort of like the parts of an address. When you give your address, you have a number, a street, a city, and a state. This is really just like the state, and you need more detail in order to get a package delivered. So we're going to start with the principal quantum number, and then we're going to define what is called the angular momentum quantum number. And that is given the symbol L, and that's a lowercase cursive l. That's sort of like the city address, the city level address. Then we're going to define the next two, which are m sub l and m sub s. These are the magnetic quantum number and the spin quantum number. And we'll now describe what each of these mean. The way we're going to describe what these mean is by first making a column here labeled location or property described, because you could think about it as describing a location, like what shell is the electron in, or you could really think about it as describing a property, because we'll learn later that some of these numbers really describe property more than a location, because electrons tend to not be located in space the same way macroscopic objects are. So what is the location described by the principal quantum number? That is what we call the shell or the energy level. Both of those words are totally acceptable and they're both used. But what we're learning now is that within shells, there are subshells. And so we're going to not really ever use the word angular momentum quantum number, but we will use the word subshell or sublevel quite often. So we should know that electrons can be found in shells, but those shells are further divided into subshells. The next quantum number is going to describe the orbital. And earlier I described that an orbital is really just a region of shape or space where an electron is likely to be. So it's defining sort of a probability map in three-dimensional space where you're likely to find an electron. And those shapes have, orientation and a specific shape. The last quantum number is the spin quantum number, and we're going to describe each of these in a little bit more detail now. We've already learned a little bit about the principal quantum number. The principal quantum number, first of all, we're going to put some bulleted statements here. Can be n equals 1, n equals 2, n equals 3, all the way up to, well, any number really, but we typically don't think about it as higher than 7 because there's only 7 periods on the periodic table, and we'll see later why that statement makes sense. Another sentence that I want to write here is that a higher n value is higher energy. And that a higher n value is further from the nucleus. So as we get further and further from the nucleus, the n value is going to show that. So first shell, second shell, third shell corresponds to higher and higher energy. And that's why if an electron falls from n equals 5 to n equals 2, that's a drop in energy. It's going from high energy to low energy, so it loses energy in the form of light. And if you want to promote an electron from n equals 1 to n equals 3, then energy needs to be put in. The statements that I want to make about the subshell, first of all, are what values this can be. And we can write that this value for angular momentum quantum number can be 0, 1, or 2, or 3. But more importantly, these are also known as S, P, D, and F. And I'm going to underline that because we typically don't refer to the subshell by number. We refer to it by these names. Is it an S subshell electron? Is it a P subshell electron? And so on. The other statement that we want to add here is that each shell has n subshells. And I'm going to put an asterisk here because we're going to develop that idea a little bit later. Each shell has n subshells is referring to the fact that the first shell only has one subshell. It happens to be an S. The second shell, n equals 2, has two subshells, and they happen to be an S and a P. The third shell, n equals 3, has three subshells, an S, a P, and a D, and so on. And of course, the fourth shell has one of each, S, P, D, and F. Let's talk about the orbitals, which are really regions of space. And the magnetic quantum number describes the orbital. And it's true that these are numeric values. We call them quantum numbers for a reason. And we don't really concern ourselves too much with the numeric value of these. But it's true that they can be any number between negative L and positive L. So, for instance, If we're talking about the number 2 angular momentum quantum number, in other words, the d subshell, then the magnetic quantum number can be -2, -1, 0, +1, or +2. That's 5 different values. And that's why the d subshell has 5 different orbitals. But more importantly, an orbital, we want to remember, is a region of space. That's really all an orbital is. It's describing a region of space where you are likely to find an electron, sort of like a probability map. Each of these regions of space have a shape and an orientation. And it may be helpful to look at a few pictures of these. Here's some of those shapes and orientations of different orbitals. These happen to be orbitals of the F subshell. And here's another summary of some of those shapes of these different orbitals, or the shapes that different orbitals describe. S orbitals are spherical. P orbitals are sort of like these polar dumbbell shapes that can be oriented on either an x-axis, a y-axis, or a z-axis. And the d orbitals have even more interesting shapes. Let's finish up our last level of an electron's address by describing the spin quantum number. And the spin quantum number can be either up or down. And if it is up, then its value is +1/2. And if it is down, then its value is -1/2. Most importantly, only 2 electrons can occupy an orbital. And this has to do with what we call the Pauli Principle, which is that no 2 electrons in an atom can have the same 4 quantum numbers. So you can't have 2 electrons in an atom which have the exact same address.